We're going to continue on where we left off with non-ideal amplifiers. And today we'll look at a few concepts such as common mode and also the frequency and bandwidth of these amplifiers. So for review, lecture 8, we looked at voltage injection, current injection, and also last time we did a little more investigation to see what was going on here. And a couple of you presented me like a really great solution to this, so I'll go over that today. We also looked at distortion harmonics last time. And so for the very last lecture, we looked at this offset voltage and what that meant. Here's like the range of that. It's really small value from microvolts to millivolts. And we talked about different kind of ways to look at that. And if you really want to get rid of that, one thing you can do is attach a potentiometer. And here is a typical type of op amp. And if you look at the ports, you can attach a potentiometer to this and sort of get that offset to zero. Now I can imagine too that sometimes you actually may want to have even a larger offset, or even change it over here depending on what type of signal you have coming in. And maybe you actually do want clipping, so you might want to change it for that reason too. But that's how you do that with the potentiometer. So the coverage of this lecture concepts, we're going to look at input bias and offset current, look at the voltage and current limits, common mode, rejection, input resistance, and also a few things regarding that kind of stuff, and then look at frequency response and bandwidth of an operational amplifier. Okay, so here's the idea that was presented in class last time to me by a couple of you guys, is looking at this like a voltage division problem. Because remember, the problem that we had in class was that, well, we didn't understand where this came from, and we still don't. There's negative wire here. But this part now makes a lot of sense. Okay, so the idea is that you would look at, okay, so this path right here is what is going on right here. So if you look at this, we're starting off at this ground here, right? And we're going through this op amp right here, and then going through this voltage. Sorry. Yeah, so we're going through that voltage right there, right? And so the thing is that even though you see your, if you follow this path around, you're saying, hey, you know, you're going through R2 first before you go there, or in this case, is RB. The voltage you're really concerned with is V1. So it doesn't really matter what voltage change you go through, if you go through this one first or that one first, because the order of addition doesn't really matter, right? Because you're really concerned with what is the voltage after you've gone through both of those. It doesn't matter which order they are in, okay? But that's a good way to think about it, because then you can combine these two voltages together. It just makes more sense if you do it that way, because you combine these two voltages together, and that's what you're getting here in the numerator. It's this voltage plus this voltage, which is negative AV1, okay? So that's this part right here. The voltage you're concerned with is right here, okay? You can approximate this as zero current going this direction right here. And also, because this is not ideal, you're not going to assume that these two voltages are the same, okay? So, so the voltage below that is this RA, and the entire resistance through that path is the RA and RB, okay? And that's what you get right here. Okay, so here's what you get by voltage division. And remember, this is what we did last time using a different method, and that's just saying that V1 equals I, instead of negative I, this equals I, and then we found out what I is, and that's just this voltage minus that voltage over RV. So it's this voltage right here, which is the negative AV1 minus the voltage at V2 right here. So it's just this I just going through R2. In this case, R is represented by R2 here. Okay, and that RA just came from this side. Right? And if you do that, you get the same results. So this is what, this is by the voltage division right here, and this is that other equation, just looking at Ohm's law for that right there. And the reason this works out, as far as I can see, is because they're not using this, right? I don't see where they're using this negative I anywhere, so only this is used, and everything else seems to make sense from this part on. And that's, so I'm getting more confident that that's a typo. Okay, and yeah, and we went through this step by step to figure out that you're gonna get the same answer in both cases. But what's really nice about this is that this is sort of like really forcing you to even understand more the different kind of ways that voltage division can appear, because it's not intuitive at first. I mean, if you do it like this, that could make it more intuitive to you, but looking at it like this is not really intuitive. But if you can see the connection, then you'll be able to easily more apply it later on when you have, well, when you know, sometimes it may be advantageous to apply it later on in a different kind of situation that's sort of like this. Okay, so so from that on, we do our current injection type, and we went through that last time too, and that looks like it all checks out. And then once you have both of these, this is the loop gain according to the voltage injection. Here's the loop gain according to the current injection. And so solving these two for the two unknowns of T, right here and here, and this ratio, which is right here and right here. I know they're inverted, but you know, you're treat that whole ratio as an unknown, and then this is what you get for those two things. Now, I did ask the book author about why this is treated as V2 over V1 instead of V1 over V2. Like what's the reason behind that? And he says, he's on vacation in wine country, so he's going to get back to me. So as of right now, we just don't know yet. But hopefully, we'll know soon the reason why for that. But you really got to honor your vacations, you know. I mean, if it's going to be a vacation, you want to really take off. Okay, so on with the new concept. So let's discuss a concept called input bias and offset current. Okay, so it says here for op amps to operate, they need small DC bias currents at each input terminal. So here's the non-inverting input terminal and the inverting input terminal. And so for these things to operate, it's like, because you have lots of things inside going on. Here, open one up, right? You need input currents. And previously, we've been saying that they're like really small and negligible, but they're needed to really operate the op amp. Okay, so for the op amps that are made of BJTs inside, the bipolar junction transistors, the bias currents are the base currents of those. Okay, for op amps made of MOSFETs and JFETs, the bias currents are the gate currents in those. Okay, and so these bias currents, they are an additional source of error. If you have like a really sensitive kind of system, here's like another source of error you have to worry about, and we're going to talk about one way to reduce that error too. Okay, so the bias currents, IV1 and IV2, are similar in a small magnitude coming in here. And the directions, they depend on the internal amplifier circuitry, the NPN, PNP, NMOS, or PMOS. So those affect the directions of these, right? But if you look at the manufacturer information that comes with op amps, they will give you the maximum offset current, like the magnitude of that, but not the sign of it, okay? And so just to be clear, so here's the input for the non-inverting node, IB1. Here's like the current, the input bias of the inverting node. And the difference between the two, IB1 minus IB2, the difference going from here to here, is your offset current, okay? And that's what this is, the difference between the two. And remember, this value is going to be given to you on the spec sheet, but the sign of this is not going to be given to you, okay? I assume it's measurable, but that's not typically given. Okay, so let's look at the voltage error due to the offset current. So remember, you have this offset current going in here, and that's going to produce an error right here at the output. So this picture looks kind of weird, but I think what the author is doing is just these currents, you know, they're inside right here, you know, they're going inside. But here they just pulled them outside. We've seen that before when we look at, you know, the RID being pulled outside. So even though these are outside the triangle, maybe because of size constraints, I don't know. But just assume that this piece right here that's connected here, that is actually, it goes to this inside, okay? And it goes to ground, right? See how they both go to ground. So that's what's going on here. It's going to ground. So this is just an attachment, but you know, ignore it because now this current is outside and it's going to ground right here. Same with this one. Okay. So let's try to find out what the voltage is right here due to these things. And you guys are aware of superposition, where you look at one source and see its effect by turning off all other sources, and then you swap it out. You turn on the other source and turn off all the other ones. So that's what we'll do here. So first we'll look at the voltage V out just due to IB2 alone, right here. And that means that we'll have to turn this one off. And if we turn this one off, does it turn to a short circuit or an open circuit? Open, because it's a current source, right? So it becomes open. Okay, so if that's open right here, then all we have is the current. I mean, this voltage out here only due to this current going through R2. Okay, because the reason why is if that's ground and there's no current going this direction. This is going to be ground, and that's going to be ground. So if that's ground and that's ground, then there's no current going through R1. I mean, there's nothing to motivate that, you know, charges to go through there. You know, it's grounded on both sides, and so you know, so you're going to have this current, you know, go in this direction right here, where none of it's going to go this direction. It's not going to go through here down to ground. Okay. That's where we get this from. Now on this one, the contribution to V out just from IB1, which is this one, that means we're going to turn this one off. So this becomes an open circuit, okay? And so that's off. So this one right here is negative IB1 RB right here, and this piece right here. You guys see where this part comes from? Right here? This 1 plus R2 over R1? No? Well, you know the resistors are from this side right here, right? So, and initially you may think, well, that's, you know, why can't the current just, you know, go this direction right here, just, you know, loop around like that, right? Well, if you look at that, and this is sort of like similar to what we discussed earlier, this looks a whole lot like voltage division, right? This type of form right there. So, one way to look at this is say, well, the voltage right here is based on the voltage right here. Okay, and that voltage, you can see that from voltage division, right? So let's work it out. Okay, so let's look at this voltage right here. So this voltage, let's call that V minus. That's going to equal the voltage, going through this path right here. So it's going to be your R1 divided by the sum R1 and R2, and the voltage of where it started from, which is V out, right? That's what that voltage is. Now, over here, this IB is IB1 or 2. It's IB1. What is this right here? This is like, this current is equal to this voltage minus that voltage, right, over RB. So 0 minus this right here over RB. And if we assume that these two things are equal, right there, then if we solve for V out, if we're looking for this right here, then this V out is going to equal, well, if these two things are the same, then let me write this over here then. So this is going to be negative IB1 times RB. Right? So if we solve for V out, we just take this and put it on this side over here. So we have this negative V1 RB multiplied by this R1 plus R2 over R1. Okay, and yeah, so that's what we get right here, right? Well, you just divide both of these by R1, and you'll see that it matches up with this right here. Okay, again, just voltage division to find that, and then we match it up with right at that number right there. Okay, so now that we found these, the contributions for each one, now we just add it together by superposition to find out what the total effect is from IB1 and IB2. Okay. Oh wait, I copied this by accident. This shouldn't be here. This is summation. Okay, so but anyways, this is good over here. So this V out total is basically the voltage that we get from here plus the voltage that we get from here, and so we just add both these together. And that's what we get right there. So that's the total contribution of what V out is. And so let's look at reduction of that. Okay, so this is what we got on the last slide. And also we got this right here. But now let's look at, what can we do to RB? So one thing we can do to RV is we can choose what our RV is. Okay. Now, if we just choose with maybe some insight that this RV is really equal to this right here, which also, this looks like something in parallel, right? R1 and R2 in parallel. So this R1 and R2 over this, if you are able to dial in your resistance to set it equal to that, then if you multiply it with this, it just equals R2. Can you guys see a little trick? Where if you take this and multiply it by this, you get R2? You guys can see that? So let's see. For those who don't see it. So the first one is, me multiplying it by 1, I get that. And then me multiplying it by the other one, I'm going to get this right here. Well, that R1 is going to cancel out with that R1. And so I just have 2 of these at the top, the numerator. Right? And then I can factor out an R2, right? And what I'm left inside with is R1 plus R2 plus R2 over R1 plus R2. If I add those together, then I have R1 plus R2 on the numerator and just R1 over 2 in the denominator. So that's 1. So that's why it's just R2 left over. So that's where that comes from. And then factor in an R2 right here, you get this. And then putting it in terms of, instead of being V2 minus V1, it is V1 minus V2. We have identified that with this offset, the current offset. Right? If you recall this definition right here. The current of it is the non-inverting node current minus the inverting node current. Okay? So that's what that is, and then it stays out there. Okay, so that's one way to really reduce that. Now, the book says that if you do something like this, you can, if you let R be equal to be something like this, you can reduce that error by an order of magnitude, like a factor of 10, smaller, if you do something like that. And there's probably ways to get it even smaller than that, but this is just one of the ways right there. Okay. All right, so now let's look at what can happen. One of the problems that can happen, we already looked at what happens to this voltage right here, where it's going to cause some error, but there's some other issues that can happen too. So this type of circuit right here, if you recall, it's an integrator, right? Where you have a capacitor on the feedback and a resistor on the input coming in. Okay, so what can happen is that if you have like an integrator in your lab and it's been sitting there for a while, your bias currents that are coming in here, they're really small. So you're going to have some offset current. And remember last lecture, you also have this offset voltage right here, where those two things will contribute and they will integrate. Why are things just sitting there? And it'll get larger and larger because of the integrating, you're just adding, more and more. And what will happen is that your output, once you get there to start using it, you'll see that your output has saturated to either this value or that value, right? So one of the things you want to do is have like a reset switch where this capacitor has been charged up because of that, the currents and the offset voltages, that's been charged up. So you want to have this reset switch there, have that on, so any of that current just falls right off. Any charge will fall off before you use it. And then once you're ready to use it, you turn it on, and then you're ready to go. But the the equation that follows is right here, where you have your offset voltage, you have your contribution due to your voltage. This is what you're really interested in, but you have this contribution and then you have this contribution, which causes it to saturate. Okay. Okay, so let's move on to this common mode rejection ratio. Okay, so now real op amps respond to a signal that's common to both inputs, called common mode input voltage, IC. Okay, and so this voltage out here is equal to, you have these two voltages at the non-inverting and inverting nodes, right? So you have this contribution, right? And we've talked a lot about this, but you also have this contribution too. And so you have this amplification factor, and then you have like the average of the two inputs right here. So you have the V1, V2, and you're divided by 2. So they're like the average, like the average voltage coming in here. And so you can look at it like this, where this is just VID, the differential voltage between the two. But you have this other error part that that you don't want, and this right here is called the VIC right here, which is that common mode input voltage. Okay, so again, this is the differential mode input. This is the one that we have been using all this time. And here's a common mode input. Is the average between the two. So the difference between the two and the average of the two. Okay. And this could be quite significant sometimes. Okay, so now one way to think about this is like this right here, where you have this VIC being modeled as a voltage coming in here. And so what you have here is, a part that goes up, this VID over 2. This part right here it goes down by VID over 2. Okay, and this A right here that we typically just call A, another way of calling it is a differential mode gain, which is, some people will put like the subscript DM to signify the difference between this one and the CM for common mode. Here's the common mode gain, differential input voltage, and common mode input voltage. Okay. So so in this case right here, the V1 is going to be the VIC, the average input, plus this right here, over 2. This is going to be the VIC minus that. Now for our idle amplifier, we've been using ACM is 0, but for a real amplifier, we have to deal with this right here. Okay? And so if you factor out this A here from that, that's just a VID. But if you factor out the A from this right here, you have this ratio, where it's a common mode amplification, right, divided by A. And this is called the common mode rejection ratio, right here. Where's the A, differential mode gain over the common mode gain. Okay, and the actual sign of the common mode rejection ratio is not known beforehand, as only the lower bound is typically provided by the manufacturer. Okay. Now, here's why something like this is important. So let's look at this situation where you're looking at the voltage cross here using a digital multimeter. Okay, so this CMRR is important for many applications such as capacitive coupling of high frequency signals, high-speed computer buses, and multimeters, etc. Okay, so so let's look at this right here. So if you look at the voltage between here, this the voltage of this digital multimeter, it's going to be V plus minus V minus right here, right? Now, in this particular case, this right here, using voltage division, is going to be the voltage that you're starting from, right? And here's the resistance that you're looking over, which is this 100 ohm resistor, divided by all the resistances. You have your 3.6K, your 100, and 3.6K right here. So this whole thing right here is 0.137 volts from here to here. Okay. Now for this common mode voltage going in here, that's this plus this divided by 2 going to this multimeter. Now you can look at that. Here's a 1/2 out in front. V plus right here is the voltage right at that point. It's going to be these two resistances below, before you get to ground. That's what this numerator is, divided by the resistances of the whole thing, all three of them. For V minus, it's just this point, which corresponds to the numerator of just this voltage, this resistance over all of them. And you work that out, that's 5 volts. So this VCM can actually be greater, much greater than this VDM across here, right? So in this particular case, if you look at the common mode error, which is your VCM divided by your common mode rejection ratio, if you wanted that to be like 1% of what that is, okay, then you could just solve for that to see what this needs to be. In this particular case, if you solve for this as the unknown, basically you're going to plug your 5 volts in here, you're going to plug your 0.137 volts into here, and solve for this as an unknown. And what you get is that you need a common mode rejection ratio of greater than or equal to this amount right here. Just because you're going to have to deal with that kind of error, because this can become kind of large for some systems. Okay. So any question about this right here, this common mode rejection ratio issue? Okay, so let's look at the another issue, which is voltage follower gain error. Okay, so now initially a few lectures ago we were talking about, well, one way to measure very small signals without really affecting what you're trying to measure is just tap into the voltage and send that through an op amp, and then they'll just copy that voltage onto this without taking any current off of there, right? But there is some error associated with it. Okay. Now, ideally, you want this gain to be 0. Unity, right? But you're going to have a little bit of problem here because we do have this right here for the differential input, but we also have this common mode input too going in here. Now it's small, right? But you can have some effects. So for V out, we're going to have, factoring out the A here, this is the VID, here's that common mode rejection ratio, and here's your VIC right here. The 2 voltages divided by 2. Okay. So if you're looking for the gain of the whole thing is V out over V in. Here's V out right here, and so you're just gonna divide this whole thing by this VI here and here. This is what you get right here. And so if you're trying to calculate gain error, it's just 1 minus that ratio right here, and so this is what you're getting right here. And so since both A and the common mode rejection ratio are normally much greater than 1, you can approximate this as being this right here, where you have this piece, and that's due to the finite amplifier gain, and then you have this piece right here, and that shows that this can be, you actually want this to be quite large, or to have a smaller effect. Okay. there should not be equal sign right here. Yeah. I'll fix that in the notes. Okay, so let's look at common mode input resistance. Okay, so in this situation, what we've done is we have this RID right here, which we're used to looking at, but now we have these other two paths right here, where we have these two resistors, and this one is going to be 2 RIC, and that's 2 RIC. They're both going to ground. The values of these are typically like in the gigaohms. They're quite large. This right here could be in the mega ohms. So very small current is going through here. But when a purely common mode signal VIC is applied to an amplifier input, VID is 0. Total resistance presented to the source is 2 RIC in parallel with this 2 RIC, which is RIC, where RIC is the common mode input resistance. So what that means is that if this voltage equals that voltage, then you can ignore this branch right here, and you can sort of pinch it together, and then you'll see that these two are in parallel. That's what's going on right here. Okay, so that's what that means. And then normally, of course, this is like gigaohms, that's like mega ohms, so this is much, much greater, 1,000 times greater. For a purely differential mode input signal, the input resistance is more like this. Rn equals this RID in parallel with 4 RIC. Okay, but that's the input resistance. There's also the concept called power supply rejection ratio. And so, just so you guys know, about this, so this power supply voltage, they can change due to long-term drift or noise on supplies. So equivalent input offset voltage changes in response to power supply voltage changes, and this PSRR measures the ability of amplifier to reject power supply variations. It also indicates how offset voltage changes in response to change in power supply voltages. So you're going to have one for the positive side and one for the negative side. And so this is just your voltage offset divided by your supply on the positive side, and this is your offset voltage divided by your supply on the negative side. Okay. And also both of these, the common mode rejection ratio and the power supply rejection ratio, they fall rapidly with frequency increase, which we'll discuss next. Okay, so frequency response and bandwidth. All right, so so previously, we've been looking at these as maybe like infinite bandwidth kind of things, but they don't really have infinite bandwidth. They have a range that they operate normally over, and then after that they attenuate. And the reason why is because each component inside of the op-amp, it has parasitic capacitance, and that's going to limit the bandwidth of the op-amp. So, and what I mean by parasitic capacitance is like this. So, okay, so let's say you have this op-amp right here, okay, so let's talk about it with respect to things outside the op-amp. Parasitic capacitance happens everywhere, right? So all these components, you could think of it as, there's a little bit of parasitic capacitance between this and ground, everywhere. And the reason why is that even if you don't have an explicit capacitor, it's really there anyway, because you have these conductive parts, and these conductive parts, they have fields, they're able to store charge, even though it's very little bit. You have lots of these components, and each one, you could think of it as an imaginary tiny capacitor that's associated with every single component in your op-amp, in your circuit, or even between things. For example, you have these two wires here. There's this parasitic capacitance between the two wires. Where this is some C key, right? So even if you have like lines close together, you know, there's capacitance between them. So, and that's going to cause some issues, right? So these general purpose op amps, they have this low pass character where you have high gain at DC and single pole response. So it looks sort of like this right here. High gain, but you have the single pole response, so it falls off. That's the 3 decibels down point right there. And if you look at the magnitude, it looks like this, where this square root of this squared plus that squared is the magnitude of this, right? Substituting j omega in for s. And then we could put it in this form right here, where that's the loop gain, that's the open loop gain. Here's the open loop bandwidth of the op amp, and this right here is unity gain frequency, or the gain bandwidth product, frequency at which this equals 1. And that is, you see here, here's omega t. That's the frequency at which the amplitude equals 1, the magnitude of that. And this is at the 3 decibel mark right there for the band. Okay, and quickly, the last slide. So what I want to talk about here is just something called the gain bandwidth product. Okay, so at high frequencies, this right here, it starts looking like this, just omega t over omega. For high frequencies, it just falls up like that. Okay, and the gain bandwidth product is going to be this times omega. So you're just taking this piece right here, multiply it by omega, it's just omega t. That's the GBW. Okay. Yeah. So and that's the reason why this omega t is also called the gain bandwidth product. Okay. All right, guys, that's it for today. I'll see you guys on Friday.